A very important application of this whole idea of mathematical induction is that it can be used to summarize large sequences through their sums. And here are some more examples. Mathematical induction has been used to prove and validate these formulas for the sums of powers of integers. I'm listing through the fifth power here. You'll notice we go from 1 to n in every case, and the only difference is the exponent that I'm raising my integer to. And mathematical induction allowed mathematicians to rewrite a summarized form on each of these that help students or mathematicians who might be working with these kinds of sums to make these calculations much, much simpler than having to square or cube each integer and add them all up. These formulas are probably something you might want to write down and make note of so that you can use them moving forward. So here is an example of finding the sum of the first 7 integers when they're cubed, or finding the sum of the first 4 integers when this difference of 6i and 4i squared are part of my sum. I want to use the formula for the sum of the cubes of the first n positive integers that we were given. Remember that the sum of integers cubed is n squared times n plus 1 quantity squared over 4. I'm going to plug in 7 because that's the number of terms I have in this summation. Do this product, and I find that the sum of all of those integers, the 7 integers cubed, all together is 784. That's certainly easier than cubing each integer and adding them all up. In the second case, but remember that the sum of a difference, or the sum of a sum, is the sum or the difference is separated. So I can sum my 6i and I can sum my 4i squared. That means in the first case I have 6 times a sum of integers 1 through 4 to the first power minus 4 times the sum of the first 4 integers squared. I plug in two formulas, formula 1 and formula 2 here, and I multiply the first formula by 6 and the second formula by 4. I get 6 times 10 minus 4 times 30. That's just 60 minus 120, and the sum of this thing for the first 4 terms is minus 60, just using those formulas. Another example of building models is an example using finite differences. The first differences of a sequence are found by subtracting consecutive terms, and the second differences are found by subtracting consecutive first differences. So here's the example. The first and second differences of the sequence 3, 5, 8, 12, 17, 23, and so on are as follows. 3 and 5, I take the difference, I get 2. 8 and 5, the difference is 3. 12 and 8 is 4. 17 and 12 is 5. 23 and 17 is 6. I then take the differences of these two terms. 3 and 2 is 1, 4 and 3 is 1, 5 and 4 is 1, 6 and 5 is 1. Notice that when I took this second set of differences, all of my values, all my differences were the same. In this sequence, because the second differences are all the same, this sequence will have a perfect quadratic model. If the first differences had all been the same, this sequence is a linear model because the pattern would be an arithmetic sequence. But I had to go to the second set of differences to find the differences were the same, and now I'm going to be able to find a quadratic model for this sequence. I know from the second differences that the model is quadratic, and so a quadratic model has this form. A sub n is equal to a times n squared plus bn plus c. By substituting 1, 2, and 3 in for n, I can obtain a system of 3 linear equations in 3 variables. A sub 1 looks like this. This gives me 3 distinct quadratic equations that I can then set up as a linear system of equations in terms of a, b, and c for my system. The first one's a, b, and c equals 3. The second one was 4a plus 2b plus c equals 5. The third one was 9a plus 3b plus c equals 8. Now I'm going to solve this system, and I can certainly do it using my matrices if I choose, and that's a good way to do it actually. And I'll find that my solution is that a is 1/2, b is 1/2, and c is 2. That means I can go back to my generic model, a sub n, and find this quadratic model, 1/2 n squared plus 1/2 n plus 2. If I go back and check values of a sub 1, a sub 2, and a sub 3, I'll find that it works. So this is another way that I can generate a pattern or a model for a sequence that may not be obvious right at the beginning. Let me know if you have any questions.